Evening, everyone, and welcome to our live stream for Paper 2 Chemistry. Now, what we're going to be doing is going through all of the Paper 2 Chemistry stuff, so that's Units 4, 5 and 6, and this is going to cover, obviously, the Triple Science and Combined Science Foundation and higher content. As always, we do have the chat window down there. Keep it respectful as we go. Basically, it's there for questions. It's far easier if you don't then post lots of other randomness, then I will miss questions. Okay, without further ado then, let's get started as this one is quite a chunky topic in total. So, Unit 4, the thing I like to refer to as groups and colours topic. What we do first of all in Unit 4 is we dive straight into some of those key groups from the periodic table that we need to know about. And the first one that we hopefully know quite a lot about is Group 1, the Alkali Metals. So the alkali metals, if you remember, far left-hand column on the periodic table there. You get a periodic table in your exam, so you don't need to memorize the names of them or anything. Just know, first column, this is the alkali metals. Key thing about them is these are very reactive, and they're going to react with both oxygen and with water, which brings us really nicely into how we store them. When you've seen them in that little demonstration in class, they would have come in these little pots that are actually filled with a liquid. That liquid is oil. The reason we store them in oil is it prevents them reacting with the oxygen and the water that's present in the air around us. Because they're metals, they do have typical properties of metals. They're shiny when they're freshly cut, they're good conductors of electricity, and they're solids at room temperature. But we also will notice that they've got three key trends that we need to remember here. First one, as we go down the group, then they get softer. So when your teacher tried to cut lithium, it was probably a little bit of a challenge with the scalpel. By the time they were down to potassium, literally just a light pressure and it slices straight through with no issue whatsoever. So softer the further down the group we go. Their density will increase the further down we go, and their melting point will decrease the further down we go. So we've got our key patterns there, first of all, as far as the alkali metals go. We need to know about three of them, and this is in terms of a demonstration that you should have seen when you were in class. Now, hopefully you all saw this. Your teacher probably had some giant glass bowl of water. There was probably some universal indicator thrown into it, and then they chucked in a little bit of alkali metal in turn for lithium, sodium, and potassium. No others, we're not allowed them. Can't think why. So, when it comes to lithium, that was the really dull, boring one that just fizzed around really slowly on the surface, and we're all just sitting there watching how long it took to just go away. The next one was our sodium. Once that hit the water, it turned into a molten ball. Literally, it hit liquid stage as soon as it touches the water, and then it zipped around quite quickly on the surface, fizzing quite a lot. Third one, our potassium. This is the one that actually literally caught fire. As soon as it hits the surface of the water, bursts into flame and burns with a lilac flame. Please use lilac, don't use other colour names. Lilac is the one. And what we find moves really quickly on the surface, fizzing lots, and in cases can explode. So that was possibly the most exciting of the three that you did. If you had a teacher that likes to use slightly larger chunks, definitely exciting. You can even blow those bowls apart if you're not careful. So this is our first reaction, alkali metals and water. What do we have? A general word equation. Metal plus water makes a metal hydroxide and hydrogen. So all we need to do, if we know that general word equation, just swap out the word metal for whatever metal it is. So lithium plus water makes lithium hydroxide and hydrogen, etc. You do also need to know the balanced symbol equations for these. So by know, I mean write them. And the good news is, for those of you that absolutely hate balancing, there's a trick to this. So what we have unbalanced is this. This is using our sodium as an example. So we've got sodium plus water makes sodium hydroxide and hydrogen. Now, the trick with balancing any alkali metal and water is that we just shove a 2 in front of everything but the hydrogen. So as long as you remember alkali metals and water, 2 in front of the metal, 2 in front of water, 2 in front of the metal hydroxide, and you remember that hydrogen is diatomic, therefore it is always a little H2, you're going to get the marks every single time. Doesn't matter what alkali metal it is that we throw into water, all the same each and every time. So a little cheats way round if you're not great at balancing there. In terms of patterns in reactivity, group 1 becomes more reactive the further down the group you go. That's a simple 1 mark answer. Reactivity increases the further down the group we go. The explanation is that as we go down the group, we're getting more of those electron shells. And in group 1, 1 electron in the outer shell, remember, same as the group number. What happens is that outer shell electron is moving further from the nucleus. So, because we're going to lose that outer shell electron, the further from the nucleus it is, the easier it is to lose it. So what we basically have is when the outer shell is further from the nucleus, the force of attraction between the nucleus and the electron is weaker, therefore it is more easily lost. So the reactivity is higher. Further down, reactivity increases for group 1. On to our second group then, we have group 7 on the right hand side of our periodic table this time. These are called the halogens. Now, if you remember very little else about the halogens, please remember that they are diatomic. This means whenever you write a balanced symbol equation with a halogen, you're going to write its little symbol and a little 2 in the bottom right. If you don't know that, you are going to mess up every single balanced equation involving a halogen. Because the thing is, these are usually worth 2 marks, 1 mark for your formulas, 1 mark for the balancing. If you don't remember the little 2, formulas are wrong, balancing is going to be wrong, it's a big 0. So Cl2, F2, Br2, I2, At2, little 2 in the bottom right every single time. Remember it, do it. Okay, other things we should know about the halogens. When we start at the top of the group, we're starting off with gases. So we've got fluorine and chlorine, which are our 2 gases. We then come into our one and only liquid, which is bromine. And then the last 2 are going to be solids, the iodine and the astatine. So we start with gases, moving through the liquid, ending with the solids the further down we go. And their color gets darker. You do need to know the colors of these halogens. Fluorine is pale yellow, chlorine is green, bromine is an orange color, iodine gray, and astatine black. So they're getting darker the further down we go. Other trends that we find is that they are going to have an increase in their melting and their boiling points the further down we go, and their density will increase. Bearded dude, if you've got a question, just ask it in the chat and I will answer it when I've got a moment, okay? Now, in terms of our reactions of our halogens then, what we need to remember is the first one, metal plus halogen, makes something called a metal halide. The naming is important here. When a halogen is on its own, the ending must always be INE, so chlorine, fluorine, etc. Once it's joined to a metal, and we've got this thing called a metal halide, it must end in IDE. So please be careful if you're writing word equations or names of just the metal halides that we have changed it from the N to a D. That one letter could cost you a mark otherwise. You might have to balance that equation again, but it's quite straightforward as long as you remember the halogens are diatomic, folks. So metal halides are just salts, yes. What we find then, because we're on the right-hand side of the periodic table, as we go down that group of the halogens, the further down we go, the less reactive they become. The reason being, group 7 have 7 electrons in their outer shell. Therefore, in a reaction, they are going to gain 1 electron. So it's actually going to be easier to gain that electron when the outer shell is closer to the nucleus. The further from the nucleus we go, the harder it is to pull that last electron in. Therefore, it is less reactive. So when we're talking reactivity here, on the left-hand side of the periodic table, the alkali metals, further down we are, more reactive because it's easier to lose the outer shell electron because it's further from the nucleus. When we're talking halogens on the right-hand side, that's going to be gaining an electron. Therefore, the further down we go, the harder it is to gain the electron because the outer shell is further from the nucleus. Similar explanations, just one is losing, the other is gaining, hence the difference in their reactivities. Now, one other reaction we should know about as far as the halogens go is something called a displacement reaction. This should have been an experiment you did in class yourself. It was truly exciting. You would have had a wonderful little spotting tile. You'd have then put little drops of different solutions in those little wells and then added things like chlorine water, bromine water, and looked if there was a color change. It was probably the most exciting experiment you did in the entire time in chemistry. Now, the displacement reaction is going to take place if a more reactive halogen is present on its own. If we've got a less reactive halogen in a halide, it's then going to take its place. Hence, displacement. It literally kicks that one out and joins to whatever it was. So if we started with chlorine and sodium bromide, chlorine nearer the top, more reactive than bromine. So it's going to take the place of bromine with that metal halide. So we form sodium chloride and bromine. Dead easy to write those as word equations or balance symbol equations. We're literally flipping the halogens. All you've got to do. Everything else stays the same. If you're doing higher tier on either triple or combined, you will need to know how to do those half equations here. So this is one of those overlap bits from paper 1 that comes back to haunt you once more. So when we're talking half equations, it's what happens to a single reactant. Remember, we're focusing in on that one reactant and then basically saying, oh, electrons are gaining it or being lost here. So using the same example we just did, here's our little half equations. So looking at what happens to our chlorine, first of all, that is going to gain an electron per chlorine, okay? And because obviously we've got 2 Cl2, 2 electrons, and that makes 2 chloride ions, Cl minus. If we do the same thing with our bromine side, we start off with bromide ions, and there are 2 of them. That is then going to form bromine. There's obviously Br2, and therefore we've also got 2 electrons being transferred here. So just go careful on how you write those half equations. We're always going to have electrons going somewhere, and when we're talking halogens, 2 of them, remember, because Cl2, 1 electron per chlorine. Do you remember as well our little oil rig? Oxidation is the loss of electrons, reduction is the gain of electrons. So you might need to identify reduction and oxidation reactions there as well. Back for everyone then, our next little group is the noble gases. This is the furthest right column on the periodic table, group 8, group 0, depending on which one you're looking at, okay? Group 0 is our more modern way of talking about it. If anyone's talking about group 8, it's a bit outdated. So group 0, periodic table, are the noble gases. These are the ones that are pretty much unreactive, hence noble gases. Noble people in the past didn't really do much, they didn't contribute much, therefore they're unreactive. Now, what we find is if we've got one of these noble gases kicking around, not really going to do anything. So there's not really reactions we talk about because they don't react. Now, in terms of their properties, on the right-hand side of the periodic table, therefore, they are non-metals. Their name kind of tells us the state they are at room temperature. It's called noble gases for a reason, folks. They are all gases at room temperature. And the reason they are unreactive is they all have a full outer shell of electrons. Now, what we actually find here is because they've got that full outer shell of electrons, then they will always go around as a single atom. Okay, so they're not pairs or anything like this, always just a single atom because of that full outer shell. Key thing to remember, the reason behind them being a gas at room temperature is that they have these weak forces of attraction between the individual atoms. A halogen becomes a halide when it actually has a reaction to form a salt, okay? So when we're looking at the halogen on its own is a halogen, but when it then combines with a metal, it becomes a metal halide. Okay, that is the name of the salt. So we'd have something like lithium chloride or sodium chloride. They're all halides. In terms of trends in our noble gases then, as we go down group 0, then what we find is their boiling point is going to increase. The reason for this is those atoms are getting bigger, therefore those forces of attraction between the atoms get stronger. And their density increases because bigger atoms. Now, one thing to watch out for in these little ones about are group 1, group 7, group 0. What we've all talked about are these trends, these patterns. Now, they can very easily give you either a graph or a table with some bits of data missing, particularly related to things like boiling points. Now, what we need to do is obviously follow that pattern, but look at the data they've given you. Don't just go, oh, well, I'm just going to whack it somewhere between the two numbers that I've been given. Look at those differences and then apply the differences of the one you've been given to the missing one. Because yes, there is going to be a range if they're asking you to plot a little bar or to suggest a value, but it's not massive. It's not like the entire range between the previous and the next one. It's a smaller one in the middle. So work out the differences and then you can apply that same difference to the missing gap, basically. Right, this next bit is only for those of you doing GCSE chemistry. If you're doing combined science, you don't need to know this little bit. And this is all about the transition metals. So on the periodic table, that big rectangle in the middle, those are the transition metals. Now, first thing, they are all metals. Again, we're not lying. The name does tell us they are metals. So typical metal properties: shiny when they're freshly cut, good conductors of electricity, they're strong, they're malleable, typical metal properties there. But what they could ask you to do here is compare the transition metals to the group 1, the alkali metals. So when we're comparing group 1 and the transition metals, those transition metals are going to be stronger, they're harder, they've got a higher density and a higher melting point. So remember a couple of those so that you can talk a comparison should it come up. In terms of the chemical properties of these transition metals, then they're pretty slow to react, if they react at all. Because in that transition metal block, you're going to find things like silver and gold, etc. All the stuff we use in jewelry. We don't want that to react because otherwise some poor person goes out in the rain with their nice gold ring and it just erodes. That would be terrible. So they don't react. But the ones that do, or the one you really need to know about, is iron. So iron is going to react with oxygen and water to make this stuff called hydrated iron 3 oxide, or rust as we more commonly know it. Now, what we do need to remember as far as these transition metals go, and the reason I just said iron 3 oxide, is because that little number in brackets, and it's always given in Roman numerals, so I hope your first 5 Roman numerals are up to scratch anyway, is going to tell you the charge on the metal ion. So because that was iron 3, so there were obviously the 3 I's, then that tells us it's going to be an Fe3 plus ion. So whatever the Roman numeral in brackets is, tells you the charge on the ion. And the transition metals are a bit quirky in the fact that they can form more than one charge on an ion. So we're going to have a look at these a bit later on, but we've got Fe2 plus and Fe3 plus, both iron ions, but different charges, hence the need for the Roman numerals. When we're looking at what we're going to form when these transition metals react to form a compound, they always produce beautiful coloured compounds. These are the pretty ones. They come in purples, blues, greens, you name it. It's a veritable rainbow of colour that we can get from these compounds. The alkali metal compounds, however, they're boring. They're white or they're colourless. So there's another great difference, is our transition metal compounds are coloured, the alkali metals white or colourless. In terms of what we use our transition metals for, these are typically used as catalysts. So they are going to speed up chemical reactions without being used up themselves. So watch out for catalyst type questions. It will always start off with a certain mass, a certain color, and it ends as obviously identical mass and color, but the rate of the reaction has gone up. Right, back for everyone again, combined and triple, higher and foundation folks, we need to know a little bit about reactivity next. So hopefully we all know that the left-hand side, those metals, are all going to form positive ions. And remember, our little cheat that we can do, you're only going to be asked about group 1 and group 2 in terms of those metals. So group 1 plus 1, group 2 plus 2. If we're going to the right-hand side, the non-metals, then they're the negative ions. So group 6 minus 2, group 7 minus 1 ions. And remember, when they tell you in the exam tomorrow, you can get that periodic table and literally stick +1, +2, -2, -1 at the top of those groups. So you've got it there as a reminder. Now, with these metal ions that we're going to form, these positive ions, then we're going to see certain reactions taking place. We've got a couple more we should really know as far as our metals go. First one is metal and water. Metal hydroxide and hydrogen are the products. Second one is the metal plus acid, and that forms a salt and hydrogen. When it comes to the salt, you've got to be able to name this. So the first word of a salt is always just the metal, so lithium, potassium, whatever it may be. The second word of salt comes from whatever acid we had. So hydrochloric acid, chloride. Sulfuric acid, sulfate. Phosphoric acid, phosphate. And nitric acid, nitrate. Know those 4 endings. They're the only 4 they could ask you about. So name of the metal, then the acid. Okay, just remembering obviously to change it from just writing, I don't know, sodium hydrochloric to sodium chloride. Please remember those ones. Now, we can see a little experiment link in here because they did ask you as one of your practical tasks to look at how we could work out the reactivity of different metals from actually experimental data. One of them would have been adding it to water. And obviously, when you look at a table of results, if you've got more reactions, so you're creating more bubbles, for example, it's more reactive. Same idea with the metal and the acid. The more bubbles of gas we make, the more reactive it is. So you can just look at a table of data and pick out which one is bubbling the most reactive, which one has done absolutely nothing, least reactive, and then just stick the ones in the middle in the right order based on level of bubbling. If we want to be a little bit more accurate with this, we can collect the gas we are producing. So we can obviously do this using the old upturned measuring cylinder filled with water, displaces the water as it goes. Or we can upgrade that to a more accurate experiment, which is going to be a gas syringe. If ever you get any kind of question on a practical technique where we're collecting a gas and it's asking for an improvement, gas syringe is going to be the answer there every single time. As far as our reactivity goes, then we could create a reactivity series, okay? So we can also see a displacement reaction used for this, where we do just have a more reactive metal displacing the less reactive one from a solution. And obviously, you can just have a little look to work those out from the information in the table. Now, obviously, we've got patterns that you can pull out that we've gone through in each of those little sections. And one thing I always suggest you do is create a little summary of those key patterns for each group. So you've got like a quick check, if you like, on them. The next little bit of our Unit 4 was all about how we test for different gases. So we've got 4 gases we need to be able to test for. First one, carbon dioxide. Lime water goes from colourless to cloudy or milky. Please use the word colourless, nothing else is acceptable. So lime water from colourless to either cloudy or milky. Next up is going to be our test for chlorine. And chlorine is going to change damp blue litmus paper, red, and then white. So we've got that 2-stage colour change here with our damp blue litmus paper. Goes red first of all because chlorine is acidic, and then it goes white because it bleaches it. So therefore it's bleaching the color in our test strip. Gas number 3 is hydrogen, an experiment you did probably all the way back in year 7, which is a lit splint makes a squeaky pop sound. And finally, our 4th gas is oxygen, and our glowing splint will relight in a tube of oxygen. So make sure you know those 4 different gas tests, because they could ask you one of those on your practical kind of skills. Okay, just for those of you doing triple chemistry now, we're going to have a little look to see how we can identify random chemicals that we're given. So first up, flame tests. When we're looking at a flame test, what we're really doing is having a look to see what colours different metals produce when they burn. Now, when we're actually burning the metal, what we're doing is exciting electrons to a higher energy shell, and then as they drop back to their original energy level, then they release energy in the form of light. And the different colours are representative of the different amounts of energy they release. In terms of how we do this practical, and again, they can ask this has come up on previous papers. We start off with a little wire loop, nichrome wire loop if you want to be very specific. And we need to clean it first of all. So we dip it in some concentrated hydrochloric acid, not the usual kind of 0.51 molar stuff we give you to play with in most experiments. This is some actual acid that could cause harm. So concentrated hydrochloric acid, you dip your nichrome wire loop in it, and then you hold it in a blue Bunsen flame, and you repeat that until it stops changing the color of the flame. At that point, you have a clean loop. We are then going to dip that into our test solution, or we're going to add a little drop of distilled water and then dip it into our test powder. Once we've got our solution or our powder on the loop, stick it in the blue flame again and observe what color it goes. And this is where we're on to our fun-filled color learning, folks. You need to know these because they can even give you a 6-mark question to identify certain chemicals based on results of these experiments. So we have got 5 of the flame test colors we need to know here. Lithium is red, sodium is yellow, potassium is lilac, calcium orangey red, and copper a greeny blue color. Please learn those 5 colors because it would be really sad if it is a 6-marker on the exam. If they ask you what might cause potential sources of error in this one, the go-to answer is always contamination. So bits of the powder remaining on your loop, falling into the Bunsen burner, anything like that, sources of contamination. Second experiment, still just the GCSE chemistry, folks, is the hydroxide precipitate test. Now, what we're going to do with this one is we've got our little solution of unknown random metal, and all we're going to then do is add some sodium hydroxide to it. So you basically add, my class is a squirt of our sodium hydroxide, and then what you're going to see is you get this solid lump, this precipitate forming in the tube. Depending on what color that precipitate is going to tell us what we've got present. So again, 5 colors to learn here, folks. Iron 2 is the green one. Iron 3 is the orange brown. Copper is blue, and then both calcium and zinc are white. So how do we tell the difference between calcium and zinc? We've got a white precipitate in the tube. What do? We just add a bit more sodium hydroxide. The reason for that is that zinc hydroxide does dissolve and forms this colorless solution if we add an excess of our sodium hydroxide. Calcium hydroxide doesn't. You can add loads of sodium hydroxide and you will still have that white precipitate there. So remember the colors, remember add an excess of sodium hydroxide to the white ones. Calcium hydroxide doesn't dissolve, zinc hydroxide does dissolve. The next one we need to know is how we can detect these negative ions, okay, the anions. So we've got a few different tests we need to know here. First one, if we want to test for sulfate ions, what we're going to do is add a few drops of hydrochloric acid, then barium chloride. So our test chemical here is our barium chloride. If sulfate ions are present, we get a white precipitate in the tube. So barium chloride, white precipitate, sulfate ion. The next one, carbonate ions. These are lovely. We add hydrochloric acid. If bubbles, then we've got our carbonate ions, and those bubbles will be carbon dioxide. Third one are the halide ions, i.e. ions of the halogens. And what we're going to do here is start off by adding a few drops of nitric acid, just to remove anything else that might be present in the tube. We then add our silver nitrate solution and look at what colour we form a precipitate of. If it's white, it's a chloride. If it's cream, it's a bromide. If it's yellow, it's an iodide. So basically, we're starting off with the white at the top of that group, going through cream to yellow. So it becomes more yellow the further down you go at that point. Now, at the end of this topic, for those of you doing triple, then you need to know about these things called instrumental methods of analysis. Basically, using machines to analyze stuff, okay? They can ask us about advantages here. First thing, these are very accurate. So there's a high degree of accuracy is a first advantage. Secondly, they're really fast and can actually run 24 hours a day, 7 days a week. Humans can't do that. That would be a little bit illegal. And they're also very sensitive. So that means we can analyze tiny amounts of samples, which is great if they're very difficult to obtain, such as things from out in space. We don't have vast quantities of them. Therefore, having something that allows us to analyze tiny amounts is going to be beneficial to us. So our first technique, our first instrumental method of analysis is gas chromatography. So gas chromatography, something we looked at in module 2, and that's where we basically turn our sample into a gas as we inject it into this machine. We then have that carrier gas, usually something like nitrogen, that pushes it through this coil filled with either alumina or silica powder. Big particles going to take longer to get through. Little ones get through really quick. As it gets through that coil, comes out the other side, picked up by a detector, and this is what we get. This little readout on a screen. Now, what we can see here, first of all, is wherever there's a peak, that's a substance. So in this case, we've got 1, 2, 3, 4, 5, 6 different substances present in our sample, okay? Because they've all come out at slightly different times. We can also see that the sample in the highest quantity is this one here, F, because it's got the tallest peak, whereas A over here is in the lowest quantity. So from that, we can then work out how many substances there are and what proportions they are present in. If you want to know, obviously, the retention time, which is basically the time it takes to actually pass through that coil, then what we actually do is read off that x-axis. Okay, so that's got your time in minutes. So we can just work out the retention time, how long it's taken that substance to actually pass through the coil and get to the detector at the other side. Bit of equipment number 2 is a mass spectrometer. Now, mass spectrometers are going to actually work out the mass of atoms and molecules in the sample itself. So we can use these to actually work out relative amounts of isotopes that are present and even work out the structure of molecules. Good news at GCSE, you don't really have to do much on the working out the structure, you'll be pleased to know. So what happens here is you put your sample in and then it's going to be ionized to form these things called molecular ions. So these are basically molecules with a charge, hence molecular ion there. Now, what we do find is that as we then give these molecular ions energy, they can break up into smaller chunks. So what we end up with then are a range of different sized chunks of the molecule that we started with. As they then pass through the machine, a detector is going to record the different amounts of each of those fragments. And we get this thing called a mass spectrum. There we go. So this is our typical little mass spectrum there. The key thing to remember is that whatever peak is furthest to the right, so in this case, this line right here on the furthest to the right of our little graph, that is the molecular ion, okay? So that is the whole molecule as an ion. Easy to spot, it's always the one furthest to the right there. Anything on this side, so anything towards the left of the graph then, is going to be a fragment, just part of that molecule, okay? So when we're looking at it, the actual height of these peaks tells us the amount of that particular thing as well. Now, what we have on the x-axis is this thing called the mass to charge ratio. And quite simply, if we're looking at the mass to charge ratio of the molecular ion, the one furthest to the right, that is the same as the relative formula mass of that molecule. So on this example that we've got here, we can see that reading the x-axis, that is at 46. Therefore, the relative formula mass of our molecule is 46. So from that, we know the relative atomic masses of different elements. You can start to work out potential combinations of what this could be, particularly when you pair it up with those smaller fragment peaks as well. Okay, that is Unit 4 done. Next up, Unit 5, which is going to be rates of reaction and some calculation-y bits as well. So, first thing is just the GCSE chemistry, folks. Again, I'm afraid there's a lot of triple-only content here. We are getting back to combined as well, I do promise. So the first calculation that comes up in the triple is percentage yield. Now, first thing, common sense test when you've calculated your percentage yield. If you've got a number that is not between 0 and 100, you're wrong, because it's always going to be between 0 and 100. If it's not, you've probably put things the wrong way around or gone horribly wrong in the theoretical yield calculation. So, how do we do it? Actual yield, given during the question, it will say 5 grams of whatever was made. That's your actual. Divided by the theoretical yield, you may have to work it out. It might tell you in the question. And then we multiply it by 100. They're not giving you that formula on your exam. So actual divided by theoretical times 100 is our percentage yield here. In order to work this out then, first thing, once you've read the question, you know it's a percentage yield question, obviously, is to have a little look, and what you've got to do is calculate the relative formula masses of your chemicals, okay? Remember, relative formula mass, periodic table, add them up. Then we calculate the sum of the relative formula masses using that balanced equation. So your relative formula mass times however many moles there are in your balanced equation. To calculate your theoretical yield, it is the mass of your limiting reactant, so the one that is going to run out, divided by the sum of the relative formula mass for the reactant, and then you multiply that by the sum of the relative formula mass for the products. Then you've got your theoretical yield, actual from the question, divided by that, times 100, gives you your percentage yield, okay? If they're giving you this as a two-part question, which they can sometimes do, so you'll have like part I is to calculate theoretical yield, and then part 2, the II, is to calculate the percentage yield. If you can't remember how to do the theoretical yield, don't just leave it all blank and think, well, I can't do any of it, because there's this joyous thing called an error carried forward mark. So if you've written down something in the theoretical yield area, you know, even if you do complete rubbish calculation, doesn't matter. If there's a number on that one, that's obviously going to be wrong, fine. But if you then use that in part 2, actual divided by whatever random number you got for your theoretical yield times 100, you can still get max marks on that second part because you're not getting double penalized, okay? So just remember, calculations, always write down something. Even if one part's wrong, doesn't mean you're going to get double penalized. Okay, so next thing we need to know about then is going to be the percentage yield and reasons why it's not going to be 100%. It's rarely 100% because, first thing, the reaction may not go to completion, i.e. not everything may react in this mixture. Secondly, we might lose some product. If it's a gas, might escape and go into the air. If we're transferring liquids from one container to another, is every drop leaving? No. And some of those reactants may react in a different way reacting with something like the air, for example. Okay, so those are reasons that we won't have 100%. Okay, calculation number 2 is going to be atom economy then. Okay, so atom economy, quite simply, is a measure of how many of those atoms from our reactants ends up in the desired product, the thing we want to make. So if we have a low atom economy, only a few of these atoms make it to our desired product. If we've got high atom economy, then most of them do. To work out atom economy, quite simply, sum of our relative formula masses of our desired product divided by the sum of the relative formula masses of all products, then times by 100. So again, this is going to be a number between 0 and 100. If it's not, flip them, then you'll get it right. Okay. So those of you doing higher tier chemistry need to know about how we choose different reaction pathways. So when we're looking to see what we should use to make a certain chemical, there's pretty much 5 key things to consider. Okay. First thing is we've got the yield of our product. Higher yields, more preferable. Secondly, we've got the atom economy. Again, higher atom economy is better. The rate of the reaction, higher is better. Any byproducts we're making, minimizing those unless they're useful is always a good thing. And then finally, this equilibrium position. So equilibrium position, remember, comes into our reversible reactions, where changing the reaction conditions, we can shift that equilibrium position. So move it towards the products on one side or the other. Now, what we need to make sure of when we're picking this reaction pathway, look at the information they give you in a question and then just select whichever one you think is best. Then justify it. State which one has the higher atom economy, etc. Okay, higher tier for combined and for triple, folks. We need to know about concentration of a solution. 2 types of concentration you could be asked to calculate. Either one involving mass in grams or one involving moles. So first thing, if it's a mass in grams that we're given, it's just the mass of our solute divided by the volume of the solution. So pretty straightforward, mass divided by volume. If it's amount in moles, then it's just amount divided by volume. So basically whatever random amount, grams or moles, divided by the volume of the solution we've got. What are they going to do to make this more complicated? Probably going to give you a volume in centimeters cubed. You need to convert that to decimeters cubed. So to change centimeters into decimeters cubed, just divide by 1000. Okay, so watch out for that just in case they do it. For those of you doing higher tier triple chemistry, we need to know titrations. This was probably a fun-filled, rather irritating experiment you did in class, where you are trying to reach the little end point using your little swirling conical flask and the huge burette. Now, titration is something that we are going to use to determine the concentration of something using a neutralization reaction. So we can work out the concentration of either an acid or an alkali through this neutralization reaction. Key thing about the indicator we use, it must be what we call a single indicator. That means we've got a very clear endpoint for this reaction. So it's one of those that goes from colorless to pink. No kind of intermediate stage. It's not like universal indicator where you've got dodgy shades of everything in between. Literally one color straight to another one. That's our endpoint. Single indicators do that, like phenolphthalein. How do we do titration then? Because this is one of those practicals you should have done in class, they can ask you about this method. So let's make sure we do know this higher tier, folks. What we've got, that big glass tube thing with a tap at the bottom, that is called a burette. So we fill the burette with acid using normally a funnel in the top so you're not spilling acid everywhere. And then what you're going to use is a thing called a volumetric pipette. So the volumetric pipettes are the long glass pipettes that you had some kind of a filler. Could have been a little rubber ball thing, could have been a little plastic thing that looks like a pen with a wheel on the side. Maybe you've got the fancy ones that are the little guns that you hold the little trigger and it sucks it up, okay? But they're all attached onto a volumetric pipette. That allows us to measure a very accurate 25 centimeters cubed of our alkali, and we transfer that to a conical flask. We then add a few drops of our single indicator to the flask, give it a swirl. We then record our start volume from the burette, making sure to get to eye level with the bottom of the meniscus, the little curve you get in that burette. And then you're going to add acid really gradually, swirling the whole time. Now, what you're going to do is go down, adding this slowly. When we get to that end point, first time you do it, that rough titration, not going to be great. But it does tell you roughly where that change occurs. You record the end point from the burette, and then you're going to do this again using obviously a much more precise method, because as we get towards that end point, you're going to add it one drop at a time. So nicely mixing one drop at a time as you go, you should therefore get an accurate result. You need to repeat this, and usually you are going to need to do this 3 times with concordant titers. Okay, by that what we mean, 3 values within 0.1 centimeters cubed of each other. So the rough one probably not going to be in there, but then you need 3 others within 0.1 centimeters cubed of each other. Those are the ones we would use in our calculations. So what we then need to do is we need to work out our actual amount of our different chemicals from this. Okay, so what we've got following a titration, we know the 2 reactants that we've got, an acid and an alkali. We know what they are. We know their chemical formulas. We are going to know the volume and the concentration of one of those reactants, either the acid or the alkali. We will then know the volume of the other reactant. So from that, we can then calculate the other unknown, if you like. And to do this, we're going to hopefully know our nice simple little formula here, where we've got, there we go, our amount in moles, which is going to be our N up here. So this is our amount in moles, is the concentration times the volume. Okay, so volume must be in decimeters cubed. Okay, and our concentration is obviously going to be in moles per decimeter cubed. If you know that formula, you are going to be able to do titration calculations. Okay, a lot of people get thrown by these, and there's no need to. Yes, there's lots of little bits to work through, but you can get at least part way there, if not all the way there. So if you've got one of these calculations to do from a titration, first thing you need to do is convert any of the volumes in centimeters cubed to decimeters cubed. Just divide by 1,000 and write those down. Then, whatever we have got, both a concentration and a volume for, we can work out the amount in moles. Because if we've got a concentration and a volume, all we do, concentration, given to us in the question, times the volume, again given to us, we may have converted into decimeters cubed from centimeters cubed, multiply them together, we now have the amount in moles. So we've got that first bit with minimal stress. We then look at our balanced symbol equation for the reaction, because we're looking to see the proportions of those 2 reactants. If we had 1 mole reacting with 1 mole, whatever we just calculated is going to be the same. If we had 1 mole reacting with 2 moles of the other, you've got to apply those same proportions, either doubling it or halving it, depending on which way around it was. Once you know the amount in moles, we also know the volume in decimeters cubed, of course, which then means we can just rearrange this. Amount in moles divided by the volume gives us the unknown concentration. And that's it. That's our titration calculations. So perfectly achievable. Set it out logically as you go through, and then you're going to be able to get maximum marks on those. If you don't get all the way to the end, you're going to get some marks. So don't just leave it blank. Try to do as much as you can. Still, for the higher tier chemistry folks, you also need to know about gas calculations. So what we need to do is our volume in decimeters cubed is the amount in moles times 24. The number doesn't change, it's always 24, okay? So what this is doing is it's talking about how much space, how much volume that our gas is going to occupy at room temperature and pressure. So what we actually have then, this 24 is what we call the molar volume. So 1 mole of gas or any substance in the gas state at room temperature and pressure is going to be 24 decimeters cubed. So that's why it's always 24. Okay, back to combined and triple, foundation and higher, folks. We're on to the rates of reaction section. So it's a whole chunk of collision theory stuff now. First thing, when we are talking rates of reaction, we are looking at how quickly reactants are used or a product is made. And the way we work it out is the amount divided by the time. So usually this involves gases. This is back to our upturn measuring cylinder, improving to a gas syringe idea here. And one thing they can ask you to do is to work out the rate from a graph. So what you're going to actually get then is a little graph that's going to have your time and your volume of something on. And usually it's going to be a little curved thing like that. So what we've got is time on the x-axis, volume on the y-axis. If it then asks you to calculate the rate of reaction between 10 and 30 seconds, then what you would obviously do is between the 10, you would obviously find, try and do this here. So there's our 10 and our 30 is about there. So you find those 2 points and then all we do is we draw a little triangle underneath. What we will then have is a time and a volume, work out the sizes of those reading off the graph, and then quite simply volume divided by time. There's your rate. If you are doing sort of the more tricky version of this, then rather than giving you 2 different points to use, they're going to literally say, what was the rate of reaction at 20 seconds? So we are literally looking at just a single point on this graph here. So what we need to do then is, this is where you're going to get your rulers out, because you need the ruler, because what we're going to do is draw a tangent to the curve. So basically you need to put your ruler so it's roughly equal on both sides of it, and then extend it out. Then what we can do, pick any 2 points, pick easy ones is my advice, draw your triangle across this straight line now, and then you can work out your volume divided by time, and that gives you your rate at that specific point on the graph. So in terms of the different factors that can affect rate of reaction, first one, temperature. If we increase the temperature, we increase the rate of reaction because we are providing more kinetic energy to those particles. Therefore, they're moving faster and they are going to have more frequent successful collisions. The 4 magic words for temperature. More frequent because they're moving faster, more likely to collide. Successful because more of those collisions are going to reach the activation energy. Link back to our module 3 stuff. If we go concentration then, when we increase the concentration of a solution, we are going to increase the rate of reaction. So higher concentrations, faster rates of reaction. The reason? Because in the higher concentration, our particles are more crowded and therefore they have more frequent collisions. You're going to sense a theme to this section. The next one is pressure. This is for our gases. So if we increase the pressure, we have more crowded particles and therefore more frequent collisions. So we've got obviously a recurring 3 words in our phrasing here for these. Next factor is our particle size. Now go careful here. People mess this up by going the wrong way. If we have one big lump of substance, that actually has a small surface area. If we break it up into teeny tiny bits, that has a large surface area. So the smaller the pieces we've broken it up into, the larger the surface area will be. So what we find is when we increase the surface area, we increase the rate of reaction because there are more exposed particles. Therefore, more frequent collisions. you are going to sense this recurring theme that if you throw down this word more frequent collisions, then you are going to be well on track. The last one is all about a catalyst. So catalysts are substances that increase the rate of a reaction without being used up or changed in the reaction themselves, and they are specific to a given reaction. So what happens when we add a catalyst is we're increasing the rate of reaction because we provide this alternative reaction pathway. And the key thing about that alternative reaction pathway is it's got a lower activation energy. Therefore, more of those colliding particles will reach the activation energy, and therefore we've got that faster rate of reaction. So when it comes to those questions about collision theory and factors that affect it, number one, read the question carefully. Don't just assume if it says temperature and rates of reaction, they're increasing the temperature. Sometimes they say we're going to decrease it, in which case, reverse your arguments. Read it carefully so you're not going to throw away marks through general stupidity. So watch out for it. Okay, next little section is all about reversible reactions then. So key thing to remember about reversible reactions is, of course, the reversible reaction sign. Wherever you see that, it means reversible reaction. Therefore, we can make our reactants form the products, and the products can reform the reactants. We have both a forward and a backward reaction, is the easy way to describe it. If we are talking about a closed system, think a conical flask with a little stopper on top, then what we are going to see is nothing can enter or leave. In that situation with a reversible reaction, we reach this thing called a dynamic equilibrium. Now, what we mean by that, dynamic because reactions are still happening, equilibrium because the forward reaction is happening at the same rate as the backwards reaction. So the concentrations of all of those reacting substances will remain constant, okay? Go careful with that. Don't say that the concentrations of all reacting substances are the same, because that's wrong. They will remain constant is the phrasing to use. Anyone doing higher tier, whether that be combined or triple, we need to know about how we change this equilibrium position. So equilibrium position is just talking about, is that point where obviously everything is then happening at that same rate, further to the right or further to the left? So is it actually going to be favoring the forward reaction or the backward reaction? And this is something that we can manipulate in order to make more of a certain product that we want. So the factors we need to know and their effects. This is still just higher tier, folks. First one, pressure. If we increase the pressure, the equilibrium position moves in the direction of the fewest moles of gas. So what you do is you look at the balanced equation, you then count up how many moles are on the left of the arrow, how many moles are on the right of the arrow. Whichever one is the smaller number, if we increase the pressure, it moves it in that direction. So we always describe this as moving to the left or the right, by the way. Second factor is our concentration. So if we increase the concentration of a substance, the equilibrium position moves away from that substance. And then finally, temperature. If we increase the temperature of a substance, our equilibrium position moves in the direction of the endothermic change. So in our reversible reaction, one side is going to be exothermic, the other direction is going to be endothermic. Now, if they've given you a little, normally they'll write the balanced equation and then after it in brackets, they'll put delta H equals. If it's a negative value, that means that the forward reaction is going to be exothermic. Exothermic always has that negative. If it was a positive, the forward reaction would be endothermic. So once you know what the forward reaction is, you can work out what direction increasing temperature goes. So the next thing we need to know then is when we come to select these conditions for one of these reactions, we generally have a compromise situation. Because what we're going to find is, yes, we could keep increasing the temperature quite significantly, but there comes a point when actually it's just not cost effective or not safe. Because, okay, we'd be moving it towards our desired product more, but you're going to then be having the energy costs to increase the temperature. If we're talking pressure, we've got energy costs, or we're going to sit there looking at the potential risk of high pressure vessels that they've got to obviously not rupture or explosions happen. So just think about that balance, that compromise between increasing the amount of product we want, but balancing it with the costs and the risks associated with generating those conditions. Okay, that's module 5 done, folks. So, module 6 to go. Right. First bit of module 6 is just for those of you doing triple chemistry, but it is foundation and higher folks that need to know this. So, first thing that we need to know is we are talking about plants. I know, in chemistry, who'd have thought? When we want to grow our plants, they need these things called essential elements, which are the elements they must have in order to grow. 3 we need to know: nitrogen, phosphorus, and potassium. So, if we don't have enough nitrogen, we get a rather sadly growing plant, doesn't grow very well, and it's got yellow leaves. A lack of phosphorus, we get these discolored leaves and poor root growth, and a lack of potassium means discolored leaves and the fruits don't grow very well. So all of those are going to create problems for us if we were farmers. So what do? In order to actually replace these minerals that we're losing from the soil as plants grow and we remove them from the area, then what we are going to do is use fertilizers, chemicals to replace the essential elements to the soil. So first thing about these fertilizers, they've got to be soluble in water. They've got to dissolve in water. You are not going to be able to take up a lump of solid through a plant root. It has to be dissolved in water to be absorbed through those roots. Now, in terms of what we're going to find, we can have a range of different chemicals in these fertilizers, and it's going to be different proportions of nitrogen, phosphorus, and potassium in there. So we have these things called NPK fertilizers, N for nitrogen, P for phosphorus, K for potassium, that will provide those essential elements, but the ratios will vary depending on what fertilizer we have got. If they give you a question saying, which fertilizer should we use for a soil that's low in nitrogen, then you'd look at the ones they've given you, count the number of nitrogen atoms, whichever one's got the most, that's your pick. Now, in terms of how we make these fertilizers, then we are going to need to know about this thing called the Haber process, because the Haber process is how we make ammonia, which is the base of a number of fertilizers and a huge range of other chemicals as well. So the Haber process is this. We are going to be starting off with 2 gases, nitrogen and hydrogen. Nitrogen comes from fractional distillation of liquefied air, hydrogen from reacting natural gas with steam. So we've got our 2 gases coming in. We increase the pressure first of all, and then we pump them into this reaction vessel. Now in here, what we've got are these beds of iron catalyst, and this is at a high temperature. So as the gases then pass over the catalyst, they're going to react, they will form ammonia, comes out the bottom where we're then going to cool it down. So we then end up condensing the ammonia, which we can run off. Any unreacted gases, they go all the way back in again. So we recycle those gases. We're not wasting them. They're literally going straight back in unless they formed the ammonia there. Now, what we do need to know is that this process is going to be carried out at certain conditions: 450 degrees centigrade, 200 atmospheres, and an iron catalyst. Now, these won't give us a fantastic yield. We could have used different temperatures and pressures, but that compromise bit comes in with those reversible reactions to basically get it to an effective amount without ridiculous costs going in. Now, when we're talking about producing chemicals, we've got 2 processes that we could use: batch or continuous. Batch processes are where we're going to be making specialty chemicals in relatively small amounts. Continuous process, stuff we want in big quantities, like ammonia. Now, what we've got then is you could be asked to decide which process we should use for a particular setting. So what we really need to consider here is what one is going to fit the needs of that particular chemical. So if we think about a batch process, it's got a low rate of production, so we're only making small quantities. It's quite cheap in terms of the equipment that we need to make it, but we need lots of people working on it because every time we want to change to a different chemical, the machinery shut down, we've got to clean it all out and then start it all up again. So we've got these frequent shutdown times and need more people to actually do all of these processes. And because of that, it's not easy to automate, not easy to get computers to do it all for us. On the other side, our continuous process, high rate of production, hence we use it to make bulk chemicals. We've got a high cost of the equipment, but it's easy to automate. So we can literally get computers to run most of this process for us. That means we don't need many workers, so a small labor force, and we don't really need to shut it down. It's pretty much running 24/7 there. So the next bit for just those of you doing GCSE chemistry higher tier is you are going to be looking at how we make sulfuric acid, okay? So sulfuric acid is made in a process called the contact process, and we need 3 raw materials for this: sulfur, air, and water. Now, this is a 3-stage process that we're going to go through. The first stage is where we've got our sulfur and we just burn it in air to produce sulfur dioxide. So sulfur plus oxygen makes sulfur dioxide first of all. Stage 2, that sulfur dioxide is going to react with oxygen to create sulfur trioxide, SO3. So what we then have is stage 2, sulfur dioxide plus oxygen makes sulfur trioxide. This one is a reversible reaction. So what we find here is there are 3 conditions we need to know for this: 2 atmospheres of pressure, 450 degrees Celsius, and a catalyst of vanadium oxide. If we've got those, that means that we're going to produce a really high yield, it's about 96%. Stage 3 is actually 2 smaller stages. So we're going to convert the sulfur trioxide into sulfuric acid, but we can't just add water to this. If we were to do that directly, we would end up creating basically an acid cloud. Now, that's not going to be safe for your workers because you're basically going to be covering them in acid cloud and acid mist. That's not going to be good for their skin care routines, let's be honest. So what we're going to do is a 2-step to this last stage. First thing, sulfur trioxide is passed through concentrated sulfuric acid. That makes a stuff called oleum. Then we add water to our oleum, and that makes a large volume of the concentrated sulfuric acid. So we've removed the dangerous acidic mist creation, and we've still made the sulfuric acid at the end. So again, this is something we could look at those potential needs to change the conditions to shift that reversible reaction in stage 2, but we're not going to bother with the pressure. It stays at 2 because it's already got a 96% yield. Why would you waste the money on increasing it? Okay. Forward reaction is exothermic, therefore the backward is endothermic. So we want a relatively low temperature, but not too low to slow the rate of reaction down. Right, the next bit is just for the GCSE chemistry higher tier folks still, and this is making ethanol. So when we want to make ethanol, we've got 2 options available to us. Option 1, we're going to use renewable raw materials. We're basically using plants. So what we are doing is a fermentation reaction. So we're going to use some kind of plant material to produce the glucose for us, and then we're going to mix that with yeast. And in this process, we're going to make carbon dioxide and ethanol. Because it's plants, it's renewable, we can just plant more plants, keep making ethanol. Now, The other option is we've got a non-renewable raw material pathway, which is basically using crude oil. Because from the crude oil, we get this stuff called ethene, and ethene can be hydrated to make the ethanol. By hydrated, we're basically going to add steam. Now, steam is just water, so ethene plus water makes ethanol. In order to carry out this reaction, we need 300 degrees Celsius, 60 atmospheres of pressure, and a phosphoric acid catalyst. So greater costs involved in some ways here. Again, look at the information in a question, decide which pathway is better based on the information that you are given. Okay, back for everyone then. We are looking at extracting metals next. Combined, triple, higher foundation. Everyone needs to know this little section then. First thing, the stuff we dig out of the ground with metals in rock form is called an ore. So ores basically are the rocks that contain enough of the metal that makes it worthwhile extracting. So 3 we need to know. Malachite is copper carbonate, bauxite, aluminium oxide, and hematite is iron oxide. So to get these out of the ground, we do mining, dig up lumps of rock basically, and then we need to extract the metal. And to extract the metal, we've got 2 processes that we could use. Electrolysis. Downside here is it's expensive because it is using electricity. However, we could extract any metal at all through that process. Or option 2, we can heat it with carbon. Now that's cheaper, but it's only going to work if the metal we are extracting is less reactive than carbon. If it's more reactive than carbon, can't use that, have to use electrolysis. So we have got our first metal that we need to know about extracting is copper. So copper comes from copper sulfide in a 2-stage reaction. First thing, we're going to heat the copper sulfide in air. So that means our copper sulfide reacts with oxygen, makes copper oxide and sulfur dioxide. And then we heat it with carbon, and that means we end up with copper and carbon dioxide. So we've just formed the copper there through this 2-stage process, but to all intents and purposes, heating it with carbon because copper is less reactive. So it works. The second metal we need to know about is how we extract iron from its ore. And what we have then is a blast furnace. So the blast furnace is basically this huge bit of equipment that we are going to use in order to get the metal out. And this is it. So our blast furnace then, we start off at the top where we're going to add our stuff. So we're going to add coke, limestone, and our iron ore. We are then going to be pumping in hot air down at the bottom here. And what's going to happen, the reactions that occur in here will result in 2 things forming at the bottom. The liquid iron, which we can run off, and we also have the delightfully named liquid slag, all the waste materials that we can get rid of as well. So in terms of the stages, first thing, we're going to burn the coke in that hot air to make carbon dioxide. And coke is basically carbon. So carbon plus oxygen makes carbon dioxide. Then that coke is going to reduce the carbon dioxide to make carbon monoxide. So we're going with more carbon reacting with the carbon dioxide to make carbon monoxide, CO. And then the carbon monoxide reduces the iron oxide to iron. Now that gives us the iron bit, and we've got these impurities that are floating around in here, and that's why we're adding the limestone, because the limestone is going to react with those to form that impurities little collection, which is called the slag. And that can just be run off separately because it's less dense than the iron. So you end up with these 2 layers, iron at the bottom because it's more dense, the liquid slag on top, run them off to the 2 different taps. Third metal we need to extract is aluminium. Now, aluminium is normally found as aluminium oxide in the ground, and because aluminium is more reactive than carbon, we've got to use electrolysis for this. So using electricity to split, hence electrolysis. Electricity, lysis, splitting stuff. Now, because aluminium oxide actually has a really high melting point, what we need to do is bring that down to make it more cost effective. So what we do is we actually dissolve the aluminium oxide in this stuff called cryolite. And that pretty much halves the actual melting point of our aluminium oxide there. What we then do is we're going to put it into our electrolysis tank like so. So we have got our carbon anodes, and remember the anode is the positive electrode. We've then got our cathode around the outside, the negative electrode. And then as the electricity passes through, we're going to split that aluminium oxide into, obviously, the aluminium. Aluminium is a metal, it'll be positive, therefore attracted to the negative electrode. And the oxygen, negative, is going to be attracted to the positive electrode, the anode. Once there, forms carbon dioxide and it's lost. So that means we can then just run the aluminium off, put it in these big, basically molds, these big slabs of metal, and then we can use that for whatever we want. If you're doing higher tier on either triple or combined, remember half equations can come up here. So if we're talking at the cathode, we're going to have our aluminium ions, Al3+. They will gain electrons, so plus 3e minus, to make an aluminium atom, just Al. Whereas at the anode, we've got our oxygen ions, okay, so we've got oxide ions there. So we're going to have O2 minus because it's in group 6, and we're going to form O2, oxygen gas, and 4 electrons. Remember, if we've got O2, that means we need 2 oxide ions on the left as well. Higher tier, folks, we need to know about another process of metal extraction, which is called biological metal extraction. Now, first thing is that when we're talking about all these mines that we've used to get metals out over the years, and we then just wandered away and left them, we finished, then what we find is they can flood. Now, those abandoned mines flooding is then going to lead to this oxidation taking place between, obviously, the oxygen in the air and our metal sulfides that are present. And they're going to make sulfuric acid. So when we've got this sulfuric acid in these mines, that's going to react with the metal ores in the obviously walls of the cavern, etc. And we're going to create these soluble metal compounds. Because it's flooded, it's then just going to dissolve in the water because they're soluble, and that can then wash out of the mine into rivers, etc., and lead to some rather interesting colors. So you've got these bright red rivers, for example, which are all down to this pollution from these abandoned mines. Now, we've got this process called bioleaching, which is where bacteria are going to oxidize the iron and sulfide ions. So what that means is if we've got oxygen water present, we will form this sulfuric acid, and that is then going to release the copper ions from the copper sulfide ores themselves. So we can use bacteria to basically get copper out of these areas. Advantages of this? Well, number one, we can use these things called low-grade ores. So these are ones that only have very limited quantities of metal present there. It is cheaper than traditional mining and processing methods because we are using bacteria rather than high temperatures, etc. And they don't need special treatment. This is bacteria. They're quite happy at room temperatures and pressures, etc. Other key advantage, they're not releasing sulfur dioxide into the atmosphere as other processes do. So, bit better, sulfur dioxide is one of those gases that causes acid rain, remember. So if we can minimize sulfur dioxide, we can minimize acid rain. There are some disadvantages too. First one, it's slow. Bacteria are not the speediest of things. And we could produce some toxic substances as well. Still, for the higher tier folks, we need to know about another type of biological metal extraction, which is going to be using plants. So what we can actually do is by picking the right plant and growing it in these low grade ore soils, they're going to actually take up those ores into the plant itself. And this is a process we call phytoextraction. So we've got our field, which has got the low-grade ore. We plant our plants in there. We usually add this thing called a complexing agent to the soil as well to make it easier for them to absorb the metals. And then let the plants grow, harvest the plants, burn them, collect the ash, and then we can process the ash because that is a high-grade ore itself. Advantages of phytoextraction then, it's cheaper, there's less waste produced, and it's pretty close to carbon neutral. Disadvantages, it's slow. We are growing plants here. That doesn't happen overnight. And obviously, we may have to repeat this process several times over many sort of harvest seasons to remove all of that metal from the soil. Okay, next bit is just for those of you doing GCSE chemistry. So combined folks, you don't need to know this. First thing we need to know is the definition of an alloy. And quite simply, an alloy is where we have a mixture of two or more elements where at least one of them is a metal. Could be one metal, could be two metals, could be many metals, but we have a mixture which involves at least one metal. There are 5 alloys you need to know about. First one, steel. This has iron as the main metal in there. And this is what we typically use in construction things, think buildings, bridges, etc. Second alloy is solder. Now, this is made of tin and copper, and we use it to join electrical components together. Third one is brass, copper and zinc, and this is used in things like coins. Bronze is copper and tin, which is used in things like bells. And then duralumin is aluminium and copper, which is aircraft parts. Now, as you probably noticed there, with the exception of steel, if you're not 100% certain what metal any of those contain, seriously, just write down copper, because it's right for everything except steel. Then obviously all you've got to do is name the other metal that's present. Still, just for the GCSE chemistry folks, we need to know a little bit about why we use these alloys. So when it comes to solder, the idea is that it's going to melt at quite a low temperature. And that means we're not going to damage any of those delicate electrical components. If we're thinking brass, then this one is going to be really strong and resist corrosion. And the reason that alloys are stronger than just the elements on their own, the single metals, is because in a single metal, every atom is the same size. They slide over each other easily. If, however, we've added a second metal, then we've got some particles of different sizes, means they're not just in these perfect layers, so they're not going to just slide over each other easily. Hence, they're stronger at that point. Now, the next little section is all about corrosion and how we can resist it. So corrosion is the reaction of metal with substances in its surroundings. So some of them don't react with their surroundings at all. Think about things like gold, for example. Just doesn't react with anything in the surroundings. But others do. And the best example you're going to need to know about is iron. And we've already mentioned this reaction. It's a redox reaction, so reduction and oxidation happening at the same time. So we start off with iron. It's going to react with oxygen and water to make hydrated iron oxide, or rust. Do remember the only metal that can rust is iron, because the others have no hydrated iron oxide produced, so can't be rusty. The experiment that you will have done here would have had 3 different little test tubes with an iron nail in each of them, and then we'd have changed the conditions. So in one, we would have had just normal tap water, which was open. That has both oxygen and water present. It rusted. A second tube, you would have had boiled water with a stopper on it. That one would not rust because there is no oxygen present. Third tube would have been the one with this little powder in the bottom called anhydrous calcium chloride. Now, the anhydrous calcium chloride absorbs all of the moisture from the air. Therefore, it has oxygen present, but no water. Therefore, no rust. Whenever you're explaining these rusting practicals, it's always that one of those things is missing if it doesn't rust, either no oxygen or no water. How do we reduce corrosion then? First thing is that we can paint things. So if we paint it, we're preventing the water and the oxygen coming into contact with the metal. Secondly, we can coat it with oil, grease, or plastic. Now, what that does is, again, prevents the water and the oxygen coming into contact with the metal, or we could plate it with either zinc or tin. So all of those are doing the same thing, preventing oxygen and water coming into contact with the metal itself. For those of you doing higher tier chemistry, you obviously need to be able to talk about this in terms of half equations again. So remember, iron, Fe, is going to make iron 3, Fe3 plus, and therefore 3 electrons as well, 3e minus. And what we're going to see here is when we're talking about the differences in reactivity of our metals in terms of their likelihood of corrosion, the more reactive the metal, the more easily it loses electrons, so the more readily it's going to be oxidized. So it will corrode easier there. Which brings us very nicely onto another technique that we need to know for the GCSE chemistry. Higher and foundation folks need to know this one, which is sacrificial protection. Now, sacrificial protection just involves a metal that's more reactive than the thing we're trying to protect. So we would stick a bit of magnesium onto some iron, for example. Now, as long as those two metals are in contact, the more reactive metal will always corrode first. Hence, sacrificial protection. The more reactive metal is sacrificing itself to save the less reactive one. Now, still just on the GCSE chemistry, folks, we need to know about different materials. And the first one is this stuff called a ceramic material. Now, ceramic materials are things like brick, china, porcelain, glass, and they all have very similar properties. They've got high melting points, they're hard, they're stiff, they're brittle, they're poor conductors of both heat and electricity. And what we find is we're going to use these in things like, obviously, our houses for the bricks there, windows as far as glass goes, etc. So what we're going to then see is in terms of how we make these. To make glass, we start with sand, and then it's going to be melted and allowed to cool. If it's bricks, this is made from clay being heated to high temperatures, and the china and the porcelain, we heat the clay to high temperatures, and then we're going to coat it in a kind of a glaze before we reheat it again. So what we then end up with are these structures basically made of these lattices. Now, some of them will have crystals, others won't. So if we're thinking about our clay, we get these tiny crystals forming, which are held together by bits of glass. Whereas if we think about our glass made from just the sand, then that doesn't have crystals. So different properties have different structures there. The last type of material we need to know about are these composite materials, which are basically made of two or more materials with different properties being combined together. So what they're going to do then is give new properties than each of the individual ones on their own. Good example of this is something like fiberglass, where we've got these tiny little glass fibers embedded in a resin, or we've got carbon fiber, which is used in a lot of sports equipment there. Again, little fibers of carbon embedded in resin there. So we're putting two or more substances together here. Now, we also have concrete, which is a composite material made of aggregate, little bits of stone basically, sand and cement. So that when we add water to it, we're then going to have a chemical reaction taking place that binds all of those individual bits together. Now, concrete's pretty good in terms of its compressive strength. So when you're pushing down on it, that's pretty strong. So therefore, it's great for foundations in buildings. However, tensile strength, pretty terrible. So if we've got a concrete beam and you place something in the center of it, it's likely just to snap. Not good in a building, obviously. If we think about something like steel, this has a really high tensile strength. So what do? Combine those two. Steel reinforced concrete. So we've got basically steel bars or steel meshes with the concrete then, and that means that we've got both high compressive and high tensile strength, the best of both worlds. For both foundation and higher combined and triple, they can give you these questions every once in a while asking you what material should we use for this particular purpose. In that scenario, they're giving you a table of information. Think about what properties are necessary for that particular function, and then find the one that matches closest. When you're then writing down which one you would pick, always start and say, this one has the following properties that means it's not suitable. This one means it's not suitable because of blah, blah, blah. Therefore, I would select this one because. don't forget to say which one you'd pick. Don't just go through and rabbit on about all the advantages and disadvantages of each one, and then don't say which one you want at the end. Always advantages, disadvantages for each. I would choose at the end. We then need to understand this thing called a life cycle assessment, which is this thing we refer to as a cradle to grave analysis of a product, basically. So we're thinking about every little point of its existence, from starting as the raw materials and how we get them out of the ground, through the actual manufacture of the product, using the product, to disposing of the product. Idea being that we're looking at this and thinking, is there a way we can improve this? Could we swap out this material for something else? Could we use a different fuel, something that's going to be easier to recycle at the end, for example? So these life cycle assessments are all designed to help us improve our sustainability in life. When we get to that end point of a product's life, we can either recycle it or it's going to end up in a landfill. Now, landfill is obviously bad because that's just literally throwing things into the ground and hoping for the best. We do get a lot of things like chemicals leaking at that point, which isn't good. Hence the big push on recycling things these days. Why do we need to recycle? First of all, it conserves raw materials and it's going to reduce the release of harmful substances to the environment. When we are recycling, though, we do need to think about some of the key things. How easy is it to collect? Can it be recycled easily? How much does it cost to recycle versus extracting? So there's a few things to consider there. The things we need to know how they're recycled is metals. They're melted and then poured into molds. They're the two things to know. Any metal, melt it, pour it into a mold. Paper, we're going to mix it with water and then clean it, roll it and heat it to make some new paper. Glass, we melt it and we mold it. And then polymers, the plastics, will be melted and molded into new objects again. So again, if in doubt on recycling things, metals, glass and polymers, melt it, mold it. The only one that's different is paper. Okay, on to just the triple, folks. We're now on to our fun organic chemistry section. So, first thing, we have got 4 different groups of chemicals we need to know here. The first one is alkanes. Now, alkanes are a version of a hydrocarbon, and hydrocarbons are made of hydrogen and carbon only. Now, the key thing about our alkanes is that they are all going to be what we call saturated. This means they only have single bonds between all of the atoms within their structure. We do need to know the general formula for our alkane, which is CnH2n plus 2, because that allows us to work out the formula for any alkane, whatever it may be. You also need to know how to name them. So we need to know the prefixes, the first bits of the names, which is just how many carbons there are. So 1 carbon, meth, 2 eth, 3 prop, 4 bute, and you can go on pent, hex, etc. Then the last bit of the name, because it's an alkane, Ane. So if we had a 3 carbon alkane, it would just be propane. We then need to understand our combustion reactions as far as alkanes go. So complete combustion is where we are just going to end up with carbon dioxide and water, whereas incomplete combustion, carbon, carbon monoxide and water formed. Obviously, carbon monoxide is that odorless, tasteless, colourless gas which can obviously cause death. The second family of our hydrocarbons we need to know about are the alkenes. Now, alkenes are unsaturated, which means they've got at least 1 double bond present. And that will always occur between carbons. So you've got a carbon double bonded to another carbon. That's its functional group, its kind of defining feature. If they ask you what is the functional group of an alkene, literally C double bond C. So all you got to do. Now, these alkenes have the general formula CnH2n, so similar to the alkanes, but without the plus 2 at the end. And what we are going to find is they've got a few reactions we need to know. Complete combustion, same as the alkanes, carbon dioxide and water is only formed. Incomplete combustion, carbon, carbon monoxide and water. And then we can have addition reactions, which are where basically we can stick these alkenes together. So this is where we get our addition polymers. If we need to test to see whether our two tubes of unknown chemicals are alkanes or alkenes, we add this stuff called bromine water, and that will change from orange-brown to colourless if it is an alkene. If it is an alkane, it will stay orange-brown. And the reason for that is that we start with an alkene, we're then going to add those two bromines onto it. So if they ask you to write a balanced symbol equation for this, quite simply, you start off with an alkene and Br2, our bromine, and then you just stick it all together. So literally just write it as one formula at the end. Our third homologous series is going to be alcohols. Now, alcohols have the functional group of OH, our hydroxyl, and all of their names end in ol, OL. Their general formula is CnH2n plus 1 OH, and again, our combustion reactions, the same as the others, produce exactly the same things that they did as well. However, the third reaction of our alcohols is that we can oxidize them to form these things called carboxylic acids. Our fourth and final group we're going to look at are the carboxylic acids, and these ones have their functional group of COOH, the carboxylic acid functional group there. Now, that is called a carboxyl group. And whenever you're asked these functional groups, you can write their name, so carboxyl group, or you can literally write COOH, for example. Now, these have got our general formula CnH2n plus 1 COOH. Just remember that one of those carbons is in the functional group. So be mindful when you are writing those. Don't make silly assumptions and miscount. Now, in terms of our carboxylic acids, we form these when alcohols react with an oxidizing agent. So if we'd start with ethanol, we can make ethanoic acid, for example. So we can make those carboxylic acids from oxidizing the alcohols. One thing to remember about our carboxylic acids that ties back into Unit 3 is that they are weak acids. So remember, weak acids, partially ionized ones. But because they are acids, they're going to react the same way that acids do. So metal and acid makes a salt and hydrogen. Our acid and our alkali will obviously produce a salt and water there. If we're reacting one of our carboxylic acids with a carbonate, we're going to make salt, water, and carbon dioxide. So we have recurring themes here. It's just acid, therefore it reacts the same way that other acids do. Okay, back for combined and triple, folks, we need to know a bit about crude oil then. So first thing is crude oil is a fossil fuel. Okay, so that means it's formed from the remains of dead things from millions of years in the past. So things in the sea died, sank down in the mud, became buried over many millions of years and turned into crude oil. Key thing, it's non-renewable. It takes millions of years to form. Therefore, once we have used it up, it is gone. Two other fossil fuels that we've got are coal and natural gas. So we can describe these fossil fuels as being finite. That just means that they've got a limited amount and therefore they are going to run out. They're being used faster than they are being made. If we want to use oil, crude oil, we can't just literally dig it out of the ground and then whack it in a car, because it's a mixture of a whole load of different length hydrocarbons. Now, it wouldn't work. It would create massive problems. So we need to split it up into the individual fractions. And we do this in a process called fractional distillation. So this is our lovely fractional distillation column that we need to know about. So what we're going to do is we're going to put our crude oil as a vapor into our lovely column here. Now, this is around about 350 as it goes in. Some things are still a liquid. This stuff called bitumen just comes off as a liquid straight away from the bottom. It doesn't turn into a vapor easy. The other ones, however, are going to start to rise in our column. And as we go up this column, the temperature decreases. So basically, the further up we go, we're going to hit a point where one of the longer hydrocarbons is then going to turn to a liquid. It's going to condense. So we get our fuel oil coming out. go a little bit further up, we've got our heating oil, then we've got the diesel, paraffin, petrol, and then at the very top, something that hasn't managed to go to anything other than gas is LPG. So the way the fractional distillation column works is we've got a temperature gradient, hot at the bottom, cooler at the top, and then different hydrocarbons have different boiling points. Therefore, the longer chains have a higher boiling point, and that means that they're going to remain as liquids or they're going to condense in the lower part of our column. So what we find, we can then separate it out into all of those individual fractions, which means we now have something we can use. However, once we've separated through fractional distillation, it's not perfect. We don't have enough petrol and diesel, but we have a massive surplus of things like bitumen and the fuel oils. So we use a second process then called cracking. Now, cracking quite simply is going to break these large alkane molecules into smaller ones. So it's literally breaking up a long hydrocarbon chain into smaller ones that are more useful to us. To carry this out, we need a catalyst and a high temperature. So if we start with something like octane, then we are going to form hexane and ethene, two smaller ones, more useful. So this helps us to meet that supply and demand requirement that we have for these different fractions. Anyway, so what we actually find then is this allows us to then meet all of those demands of everyday life so that we can get the right amount of each of those fractions and therefore have enough petrol to run all of our cars, at least until the crude oil runs out anyway. Right, just for those of you doing GCSE chemistry, we need to know about different polymers. So the first one, the addition polymers, these are made by two alkenes joining together first of all. Then we just keep adding more and more alkenes. So basically an addition polymer is where we've joined many alkene monomers together. To do this, we need high pressure and a catalyst. Our next polymer that we have got are the biological polymers. So what we actually have then is the biological polymer we need to know about first of all, good old DNA. Now, DNA is made of these monomers called nucleotides, and the nucleotide is made from a phosphate, a sugar, and a base. Hopefully you know that from your biology course. 4 bases, A, T, C, G, and what we are going to find is those two strands of DNA held together by the complementary base pairs through hydrogen bonds. Another biological polymer we've got are proteins made from the monomers of amino acids. And we've also got our carbohydrates, which can be created as a polymer from simple sugars joining together to make things like starch, for example. If you're doing higher tier chemistry, you need to know about condensation polymers as well, okay? So in a condensation reaction, two molecules react together to form one large molecule and one smaller one, typically water, hence condensation reaction. So what we're going to find here, to make a condensation polymer, we are going to have carboxylic acid and an alcohol. What happens is those two are going to join together to make an ester and water. So this is our condensation polymer. And what we're going to find here is these ones don't require a catalyst and they will take place just at room temperature and pressure. So what we need here for this to take place are two functional groups on the monomers. In terms of the examples you need to know, the first one is with the amino acids. They've got their two functional groups, the amino group on one side, the carboxyl group on the other. So what happens here is when they then join together, they form this thing called an amide group. So we're making polyamides. What we then have are two products that you are probably familiar with in everyday life anyway. Polyester, which is obviously something that's in a lot of clothing. Now, this is a condensation polymer made from carboxylic acid and an alcohol. Then we've got our polyamides, which are made from the carboxylic acid and an amine. And these ones are things like nylon, which is quite often in things like carpets and the like. So what we've got there are two different condensation polymers made through this reaction where we're also generating the water by joining things together. So back for foundation and higher tier triple, folks, we need to know about producing electricity in fuel cells. So what we're thinking here is how we can actually generate electricity in scenarios where setting fire to a fuel probably isn't a great idea. Think space. So when we're talking about any of our space shuttles, etc., having some kind of a fuel that we're then going to set light to is not smart, because if something goes wrong, then that's bad news for you. There's no way you can walk away to in a fire situation. So we use a fuel cell because this is allowing us to generate electricity through a chemical reaction, zero combustion occurring. So we use this thing called a hydrogen oxygen fuel cell. And you've probably seen this lovely little diagram. Now, what we actually have then is we are starting off with hydrogen here and oxygen here. So what's going to happen is the hydrogen is going to come in and it's going to lose electrons. And when it does that, it's going to become hydrogen ions. So what we see, hydrogen gas, H2, comes in, loses electrons, and forms these hydrogen ions, H+. Now, in the center here, we've got this thing called a proton exchange membrane. Now, proton is just another way of saying hydrogen ion. So basically, we have a membrane that lets the hydrogen ions cross to the other side, and these electrons are going to pass through some kind of an external circuit. And when electrons are flowing, that is obviously going to power our electrical devices. On this side, we've got our oxygen. These hydrogen ions are then going to rejoin with the electrons and with our oxygen, and what we're going to make is some water vapor at the end. So the only waste product we have at the end of this is water vapor. And if we're thinking about a space shuttle, water can then be used to drink. So very handy all round. We've got safe electricity without the risk of blowing holes in our space shuttle. And we've also got water which can be used as a drinking source. So that's how our little fuel cells actually work. Advantages of them: they're lightweight, they're compact, there's no combustion, no carbon dioxide is produced, and we're just going to be making water as the one waste product. Disadvantages of the fuel cells, though, is that most of the hydrogen that we use in them comes from fossil fuels. That's a problem still. And they also quite often contain catalysts which are actually quite poisonous and therefore have very specific disposal techniques come the end of their life. Okay, we are almost there now. We're on the last chunk, which is the atmosphere and water stuff. So first thing, when we think about the atmosphere, we need to go back a little bit in time, just 4.54 billion years, to the beginning of the Earth. So back at the start of Earth's existence, it was rather inhospitable, loads of volcanoes constantly erupting. Therefore, we had lots of water vapor and carbon dioxide being released, creating this very carbon dioxide-rich atmosphere. As Earth then started to cool down and just calm its jets a little bit, then what we found was the water vapor condensed and we started to form our oceans. So that then meant our atmosphere was mainly carbon dioxide, little bits of ammonia and methane in there. We move forward a little bit further, and what we find is algae and plants then come into existence. Therefore, photosynthesis can take place, and that means carbon dioxide levels come down and oxygen levels start to rise. Because we have photosynthesis, carbon dioxide and water makes glucose and oxygen from our biology course there. That oxygen would have reacted with metal in the oceans to make these metal oxides and then released into the atmosphere once most of that had been oxidized. That obviously eventually led us to our current atmosphere: 78% nitrogen, 21% oxygen, 0.04% carbon dioxide, small amounts of other things. So make sure you know nitrogen 78, oxygen 21, and the carbon dioxide 0.04. We then need to concern ourselves with a bit of pollution. So a pollutant, quite simply, is anything we release into the environment that could harm living things. So one of those that we've already mentioned, carbon monoxide, obviously this gas that we're producing through incomplete combustion. Big downside to it, it can actually bind to the hemoglobin in your red blood cells. It does that irreversibly. So at that point, it's got carbon monoxide rather than oxygen. You're not able to transport the oxygen you need, therefore, you could suffocate. Hence why you start to get a little bit tired initially when you're exposed. And if you don't move out of that area into lovely fresh air, then endpoint is sadly death. Second little problem chemical that we can release into our atmosphere are these things called particulates. Now, particulates are just teeny tiny little particles produced during incomplete combustion. And basically, our big problem here is when we breathe them in, then they get down into our lungs. And once they're there, they lead to conditions like bronchitis. Now, itis just means inflammation. Bronchi, where it's inflamed. So basically, inflammation of your bronchi, the tubes going to your lungs. So that means you are going to suffer with breathing problems. Hence why people are moaning a lot about things like loads of cars on the roads and causing breathing issues in small children, etc. The next one we need to know about are the nitrogen oxides. Now, nitrogen's pretty tricky to get to react. It's usually pretty unreactive because it actually has a triple bond between those two nitrogens. But inside our car engines, we get to a high enough temperature to actually create our nitrogen monoxide. That will then form things like nitrogen dioxide, and these oxides of nitrogen will go up into the air, dissolve in the clouds, and then we've got acid rain. So, acid rain problems, it erodes stonework, corrodes metal, kills trees, kills living things in lakes and rivers and the like. So acid rain is bad. Acid rain, however, and I see this every year, it's not going to melt your clothes and skin. This is not a cartoon. You do not have to think, oh, hang on, it's raining today. I'd better stay in my house in case I melt. Please don't write it melts clothes and skin for acid rain. You can have erodes stonework, corrodes metal, kills trees, kills fish. Nothing else, please. Then we've got sulfur dioxide, again created when fossil fuels are burnt, causing acid rain and breathing difficulties again. So nitrogen oxides and sulfur dioxide, acid rain is our problem. Okay, climate change. An overlap with physics. A nice overlap topic, always good. 3 greenhouse gases we need to know about then. Carbon dioxide, methane, water vapour. We're not banging on about reducing our amount of water vapour in the atmosphere because it just evaporates. You kind of can't control that. That's just life. However, carbon dioxide and methane, we can do something about. In terms of why this is a problem for us, when we increase the amount of greenhouse gases in the atmosphere around planet Earth, that radiation from the sun that normally comes down, absorbed by the surface, radiated back, and then a fair proportion would just vanish off into space, it doesn't. With those greenhouse gases, they will absorb it and then re-radiate it back down to us. Hence, the mean surface temperature of the Earth goes up and it increases. Now, in terms of who's to blame for that? Humans. Of course, it's us. Because we are burning loads more fossil fuels, we're cutting down more trees. All of that means carbon dioxide levels are going up further and further, and therefore we're increasing the rate of climate change. We've got this thing called the enhanced greenhouse effect. We're basically cooking the planet. Now, bad news as far as the impacts of this. If the temperature of our planet gets hotter, the ice caps are going to melt. That's going to lead to the sea levels rising and flooding. So those 3 go really nicely together. But we're also, in other areas of the world, going to see droughts. And we get these really extreme weather events occurring more frequently. Think about these very severe hurricanes that are happening more regularly, etc. Physics will have climate change in the paper 2 stuff as well. Now, If we're looking to see how we can do something to try to stop this, listen to what any government waffles on that they're apparently going to do, and then they don't. We're all trying to reduce the consumption of our fossil fuels. So rather than driving things like petrol and diesel cars, swap to the electric cars, etc. Rather than relying on coal burning power stations, let's all whack solar panels on our roof, etc. Anything like that is going to help us reduce those carbon dioxide emissions. But that's not going to be enough on its own. We need to protect against the effects that basically are already here. So we need to do things like building flood barriers in those regions of the world prone to flooding. We need to think about the buildings that we are creating in certain areas that are more likely to experience these extreme weather events, so they're not going to get flattened by the next hurricane that blows through. And this is our final part. We are very nearly there, folks. We just need to understand how we get water to drink. So, in terms of the original sources of the water that we are going to drink, basically think of anywhere you get water: lakes, reservoirs, rivers, aquifers, if you want to be fancy. Any of those count when they give you a "where does the water originally come from" question. Now, when it comes from things like a reservoir, then this is like obviously a huge body of water. In there, we're going to find leaves, soil, bits of animal, who knows, a whole range of stuff. Now, you're not going to go to the reservoir, fish out a cup and just drink it. At least I wouldn't recommend it. We've got to clean this up first of all before it's safe for us to consume. So what we've got, 4-stage process, which this lovely diagram sort of shows us. Here's our reservoir with all the bits and pieces floating in our water. We then pass it through our first little filtering system. So basically, we've got these big meshes that are going to catch all the leaves and the twigs, basically the really chunky stuff. Then the water carries on into this first tank, which is a settlement tank. And what we do is we just leave it in there for a bit. Anything that's heavy then sinks down to the bottom and we can run the water off. We sometimes add this stuff like lime or aluminium sulfate to it, which helps things stick together like little bits of clay so that they do sink down to the bottom. We then come to our next filtration, which are basically different degrees of sand that it's going to just trickle through very slowly, leaving some more of those particles that are floating around, obviously insoluble stuff, on the surface. By the time we're down here, all we need to do is get rid of any bacteria. So here, what we're going to do is add some chlorine, because chlorine kills the bacteria. Now, once we've killed the bacteria, off it goes to our homes once they've double checked to make sure they haven't overdone the chlorine there. Difference between groundwater, freshwater and wastewater. Wastewater is basically the stuff that has left our homes after being used. So we need to clean that up in a different process because we need to remove other potential contaminants. You don't need to know about that process on OCR, just that it is removed. The freshwater is going to be things from things like a lake. And then groundwater is where it's actually coming from underground itself. So we've got these underground water reserves, if you like, that we can tap into as well. Okay, so the final thing is not everywhere has lots of supplies of fresh water here, or non-salty water. If you're thinking about some countries around the world where they're basically island nations, they're surrounded by water, but it's salty. So we use a different process there called desalination, which is basically using this distillation process or reverse osmosis process to remove the salts and make it safe to drink, to give us that potable water, drinking water. And that is all of paper 2 chemistry. 2 minutes off 2 hours. There we go. We did it in under 2 hours tonight. So when it comes to your exam tomorrow, obviously read the question carefully. If it's anything about choosing materials, etc., do make sure you go through pros, cons, and then say what you're picking and why at the end. Don't miss that point off. Any 6 markers, there's usually 2 or 3 things to do. And remember, tick them off as you go. Make sure that you have put all of those in. If you've only done one of those sections, guarantee you're stuck at a level 1 at best. So read it carefully, use the periodic table if needed, take a calculator with you, please, and use it and show all your work in. Otherwise, Good luck tomorrow, and we've got one more of these to go, which is obviously 6 p.m. night before physics, so that is Thursday night at 6. I'll see you then. Hope the exam goes well tomorrow.